Welcome to the second lecture on sampling methods. In part 2, we'll be looking at systematic, cluster, and stratified random samples. You can find this material in Chapter 1, Sections 2 and 3 of your textbook. In the last lecture, we asked this question. Suppose that we wanted to take a random sample of size 5 from a class of 30 students. Suppose our students are seated in chairs with 5 rows of 6 students each. Would the following work to make an SRS? We could select a random number between 1 and 6, say a 2. Then we could choose that second person from each row of seats. We said that no, this is not a simple random sample, and the reason is that not all samples of size 5 are possible. For instance, we could never get a sample that selected both the third and the fourth person from row 2 of seats. The reason is we will only select one person from each row. Therefore, this is not a simple random sample. It is, however, an example of a systematic sample. These are sometimes used in informal statistics. They're easy to understand and produce, but they can be subtly biased in some situations. Now let's just review how we did this. In this case, we looked at the seating arrangement, chose the random number 2, and then took the second person from each seat. But notice there's a numerical pattern that's being produced here. After we choose the 2, if we add 6 to that, we'll get to 8. 6 more will get us to 14, and then to persons number 20 and 26 in the same way. Our textbook describes the method in this way. Divide the population size by the sample size, 30 divided by 5 in this case. Select a random number that is suitably small, call that number k, then we add the number m, which is the size of the group, repeatedly to get the rest of our sample. For those of you who are comfortable with algebra, this will make a lot of sense, but let me translate that for you in terms of the example above. We have 30 people. We divide by 5 the sample size to get 6. We then made a random choice between 1 and 6 because we're dividing our population up into groups of size 6. Then we start with a 2 and take every 6th person thereafter in the list so that we select 2. 2 plus 6 is 8. Then 8 plus 6, we select 14. 14 plus 6 makes 20. The 20th person will be selected, etc. Notice that in this case we're not making any reference to physical seating. We're simply dividing an ordered list of the class up into groups of 6 and making a selection, the same selection from each group of size 6. Now, is this generally better or worse than choosing an SRS? Why would we want to use such a procedure? And could we come up with some examples of where it would be a poor choice? Generally, statisticians say that this technique is worse, and sometimes a lot worse, than a simple random sample. These methods are used, however, because they are convenient, and also we could add because they're very easy to understand, and someone who has little knowledge of statistics may not think of another option. These kinds of samples are likely to be biased, however, if there is a pattern in the data that's incompatible with our selection technique. Let's take an example here. Suppose we have a database of students and their parents from an elementary school. So we'd have maybe our student Sarah Arnett is first, then her mother and father are listed in that order, Janet and William. Next student might be Bobby Jones, his mother Betty, and his father Jim. So what we have is a list of people that will have a pattern. The first will be a student, the second a mother, the third the father, and then the pattern will repeat. Now suppose we were to take every third person out of the list, starting with, again, say the second. Well, we'd get Sarah Arnett's mother, Janet, then 1, 2, 3. We'd get Bobby Jones' mother, Betty, and etc. In every case, we would end up selecting a mother. Well, this is far from being having the kind of representation of the list of names that we really want. So we can see that this method can go wrong if there's a pattern to the names in the list and our method of selecting names somehow matches that pattern. There is another method of sampling known as the cluster sample. In cluster sampling, we divide our population into groups that are called clusters. We then obtain a simple random sample, not of individuals, but of clusters. Then each individual or each member of each cluster is put into the sample. Suppose, for instance, that the engineering department of a light bulb manufacturer needs to do a quality study. Maybe boxes of bulbs contain 4 bulbs each, and these are packed into cases of 6 boxes, so you have a total of, say, 24 bulbs in a case. Could we choose a strategy to select a sample of around 100 bulbs for testing? But we want to do that in a way that doesn't open an excessive number of cases. So if we came up with a scheme, say, of numbering each bulb in each box, and then continued that numbering system from one case to the next, we could take an SRS of out of the 1,000 bulbs that are produced in a shift. This probably wouldn't be a very good idea, though, because likely those 100 bulbs would come from nearly 100 different cases, and this would be quite costly for the manufacturer. Well, one way of doing this would be to, first of all, take a simple random sample of size 4 of the cases. Then, once we've selected the 4 cases, we could simply test every single bulb in each of the cases. This would give us 4 times 24, or 96 bulbs, which would be probably close enough to our desired size of 100 bulbs. Here's another example of where we might try cluster sampling. Suppose a small town consists of 36 blocks, and each block contains approximately 20 homes. The town council wants to determine resident satisfaction with the city-provided trash pickup service. Describe a cluster sampling strategy to select a cluster sample of approximately 80 homes. Then think of some circumstances where this probably would yield a representative or a non-representative sample. We have this kind of a map of the city. We have 36 different blocks, and we would like to choose 4 of them for sampling. We could use a random number generator or a table of random digits in order to select those blocks. Let's suppose they turned out to be blocks 4, 12, 17, and 32. Simply interview all of the homes in each of these blocks, and that would give us 20 times 4, or 80 different homes that we've contacted. This method would probably work reasonably well as long as the blocks are homogeneous. By that I mean that moving from one block to another, we don't find a large difference in the kind of homes that are located in those blocks. It has the additional convenience that if our interviewers are working on foot, they could simply walk each block and knock out 20 homes on each block. Then they could move to the next one and continue until they've finished interviewing all of the homes that have been selected in the city. If the 80 homes, on the other hand, had been randomly scattered over the entire city map, it would take quite a bit more time for the interviewers to reach these homes. And in fact, if we're thinking about paying labor for the interviewers, a substantial amount of that labor would go into the time that the interviewers are checking their maps and hiking from one area of the city to the next. So this can not only be convenient, but could save a significant amount of money in doing the study. It could, however, go badly if the blocks are not homogeneous. By that I mean that some areas of the city might be rather different from others. Suppose in terms of income, for instance, that we have 4 blocks of relatively high income area up here in the upper left, low income area marked over in this region, and the rest of the city is of moderate or middle income homes. Now, if that were the case, you can see that our random selection of blocks took 1, 2, 3 blocks out of the low income area of the city, and 1 block out of the middle income area of the city, and none out of the high income area. So circumstances in which this cluster sampling technique would work well would be if the blocks are relatively homogeneous. On the other hand, it probably will not work well if there's a large difference in the blocks as you move from one area to the next. We'd want to be a little more careful, a little more intentional about how we choose the blocks in those regions. A way that that is done is known as the proportional stratified random sample. In stratified random sampling with proportional allocation, we first of all divide the population into subpopulations called strata. In the case of our city map, those strata would involve the low, middle, and high income areas of the city that we have pictured here. Secondly, within each of the strata, we obtain a simple random sample of a size that's proportional to the size of the strata. So back here in this map, 4 of the blocks out of the 36 are high income, so 4/36 of our total sample should come from the high income areas. In the same way, we have 12 blocks of low income area, so 12 out of 36, or 1/3 of our sample, should come from the low income area, and the remainder then would come from the middle income areas of the city. Suppose, for instance, we were trying to ask this question: should bus routes be extended into a certain portion of the city? Now, the outcome to this question is likely to be influenced by income. People who are relatively well off can afford to provide their own transportation, and in fact likely prefer that since it is more convenient. On the other hand, the lowest income members of the city probably are much more interested in mass transit because they don't have other options. So suppose the neighborhood that we want to study has 15,000 housing units. 1,500 of those, say, are classified as upper income, 10,500 are classified as middle income, and 3,000 are classified as lower income. If we want a stratified random sample of 200 people, how would we do it? Well, the answer is, first, we would divide the housing units according to the income level. We would then notice that 10% of them are high income, 70% are middle, and 20% are lower income units. Therefore, our sample should be 10% from high income areas, 70% from middle income areas, and 20% from low income areas. So we would take our sample size 200, compute 10% of that, 20 of the homes we interview should come from the high income areas of the city. Then 200 times 70%, or 140 that we sample, should come from the middle income areas of the city, and finally 20% from the low income areas. This is known as a proportional stratified random sample. Now, we've described two methods that are rather similar. The last one here is the stratified random sample, and the one before, the cluster sample. How can we tell the difference between these, or how can we choose which one should we use? Well, first of all, you want to recognize that in both cases we're taking our population and dividing it into groups, and then we're sampling based on those groups. In the case of clusters, we're taking every individual within each cluster. In the case of strata, we're taking a simple random sample from within each stratum. You also have to think about how the groups are chosen. Think about the example of the quality study for light bulbs. The clusters are chosen merely for convenience. We're taking cases of light bulbs because it's convenient to open a case and to test every bulb within it. We really do not expect that as we move from one case of light bulbs to the next, that there will be much of a difference in terms of the quality data that we get from those different cases. On the other hand, in the case of the strata, we're dividing the population into groups according to some characteristic that probably will influence the outcome of the study. In the case of the study about mass transit, we think that the income level of the families living in those areas will in fact influence their desire to have improved mass transit or not. And therefore, we do a stratified random sample there rather than a cluster sample. Let's look at one more example of a proportional stratified random sample. Suppose a college has 400 freshmen, 300 sophomores, 200 juniors, and 100 seniors. If we wanted to take a sample of these students and do it in a way that reflects their makeup among class standing, how many from each class should be chosen if we wanted a sample of, say, 120 students? What we need to do is to compute the relative size of each stratum. 400 out of the 1,000, or 40%, are freshmen. 300 out of the 1,000, or 30%, are sophomores. 20% are juniors, and 10% are seniors. We then take our desired overall sample size of 120 and multiply it by these proportions. 40% of 120 is 48 for freshmen. 30% of the 120, or 36, should be sophomores, and likewise 24 and 12 are the numbers for juniors and seniors. We then take an SRS of each of these sizes from each class. In other words, we randomly select 48 of the freshmen, 36 of the sophomores, 24 of the juniors, and 12 of the seniors. This would give us a proportional stratified random sample of 120 students that represents the overall makeup of the student body in terms of class standing.